So, in the last lecture we were discussing the spherical harmonic solutions for the Laplace equation. Okay. Okay, I told you that the Laplace equation is del square t is equal to 0. Solution expressed in spherical harmonic form is n is equal to 0 to infinity, summation m is equal to minus n to plus n, a n m r power n plus b n m by r power n plus 1, okay, p sorry. Where these functions y and m of theta and phi, okay, are basically solutions of the Laplace equation in the angular coordinates. Okay. So, if you recall, okay, the original equation was 1 by r square d by dr of r square partial t by partial r, okay, plus 1 by r square sin theta this is equal to 0 was the original equation. And if I separate out t rather than the way I had done it earlier, I separate it out into f of r times y of theta and phi. Okay. Substitute this into the equation, divide throughout by y and multiply throughout by r square. Okay. Then what I will get is 1 over f, okay, partial by partial r. I multiply by r square and divide by f times y. Okay. Plus 1 over y sin theta where y is a function of theta and phi. Okay. Now, the first term on the left is only a function of r, the other two terms are only a function of theta and phi. Therefore, both of these have to be constants. What should that constant be? Okay. When we discussed the Legendre polynomial expansion, we found out that that constant has to be of the form, okay, 1 over y sin theta this has to be equal to minus n into n plus 1, where n is an integer, okay. And therefore, the solution for this is y of theta and phi is equal to some constant. Okay. In this case, we had used a normalization constant here. Okay. So, this was 2n by 2n plus 1, okay, n minus m, I am sorry, into n minus m factorial by n plus m factorial. A constant, in order to make this whole thing orthonormalized, that is, the magnitude has to be, the inner product has to be 1, okay, times P n m of cos theta into e power I m phi. Where m goes from minus n to plus n. Is equal to for So, this spherical harmonic is a normalized solution for this equation. For the Laplace equation, the angular parts of the Laplace equation. And this thing satisfies the orthogonality condition integral d phi between 0 and 2 pi integral sin theta d theta between 0 and pi of y n m of y n prime minus m prime complex conjugate of theta phi is equal to delta n n prime delta m m prime. So, that is the solution. That is the solution for this, the part of the Laplace equation that depends upon the angular coordinates. The other part depends on the radial coordinates, and the solution for f is equal to 1 by two solutions, one which is r power plus n and the other one is 1 by r power n plus 1. So, those are the two solutions. So, what do these physically mean? So, let us examine that. N is equal to 0 implies a point source. You recall we had solved in a spherical coordinate system a point source located at the origin, which is emitting heat isotropically in all directions. Del square T is equal to 0. This was the limit as we take the radius of a sphere to 0, as we take the limit of the radius of a spherical particle going to 0. We had taken a spherical particle with T is equal to T naught at the surface and T is equal to T infinity far away. Solved the Laplace equation for a spherically symmetric particle, and we had got that T is equal to where r is the radius of the particle. And T is equal to T naught at the surface. And I could write it in terms of the total heat emitted per unit time as Q by 4 pi k r. This solution depends only upon the total heat generated by the particle. It does not depend upon the radius of the particle. Therefore, this solution is applicable even when the radius of the particle goes to 0. That is the point particle limit. It depends only upon Q. So, T is equal to T infinity plus Q by 4 pi k r. Recall the solution for the temperature that we had. T is equal to sigma n is equal to 0 to infinity sigma minus n to n of a n r power n plus b n by r power n plus 1 y n m of theta and phi. For n is equal to 0, Okay, there is only one term in the expansion for n is equal to 0. Okay. In that case, t will just be equal to a0 r plus, I am sorry, okay, n is equal to 0. So, this is just equal to a0 plus b0 by r, okay, because y and m is a constant, okay, it is a constant, and therefore, to within a proportionality constant, this is just equal to a0 plus b0 by r. Okay. So, these are identical to the terms that we have for a point source. Okay. The red term is a constant, the blue term decreases proportional to 1 over r. So, a point source is the solution of this equation for n is equal to 0. Okay, n is equal to 0 corresponds to a point source. Okay. I should note that this equation can also be written, okay, rather than having a del square t is equal to 0 outside of the point source and the temperature, okay, at the origin is undefined because there is a source there. Okay. Instead of that, I can also write the conduction equation in this case as del square t plus q delta of x is equal to 0, where q is the total amount of energy emitted per unit time. Delta of x is the 3-dimensional delta function that has dimension of 1 over volume. Okay. So, this k del square t plus q times delta of x, that is the Poisson equation with an inhomogeneous term. Okay. Q times delta of x, recall that the delta function satisfies the condition that delta of x is equal to 0 for x vector not equal to 0. That is, when x, y and z are not 0, that is, if either x is not 0 or y is not 0 or z is not 0, this is equal to 0. Integral over the entire volume of dv times delta of x is equal to 1. Okay. So, this function is going to infinity at the origin, and the integral over the surface is equal to 1, and integral dv of delta of x times some function of x is equal to that value of the function at that origin. Okay. Those, recall, were the properties of the delta function. Okay. So, how do we solve this Poisson equation here, okay, with a delta function source? Okay. How do we solve this Poisson equation with a delta function source? Okay. So, I write del square t is equal to integral of q by k, sorry, delta of x by k. Okay. I integrate it over a small differential volume. So, I have in this coordinate system, I have the point source at the origin, okay, and I take a small differential volume, okay, with volume V and surface S and integrate this. Okay. On the right side, I have integral q delta of x by k times dv. Okay. Q is a constant, it is independent of position, and so is k. Okay. Q is a constant, independent of position, and so is k. Delta of x integrated over any volume that contains this delta function, this is just equal to q. My apologies, I have missed out a negative sign here. So, let me just put that in. Okay. This equation has a positive sign on the left hand side. So, when I take q to the right hand side, I should get a negative sign. Okay. The left hand side, right, this is integral over the volume of Laplacian is the divergence of the gradient. The Laplacian is the divergence of the gradient, okay, with a negative sign here. Okay. Laplacian is the divergence of the gradient. This can be written as integral over the surface of the unit normal times grad t. This, the unit normal to the spherical surface, is in the radial direction. Okay. The unit normal to the spherical surface is in the radial direction. Okay. This is applicable for any surface, but I will just solve it for the spherical surface in this particular case. Okay. This is integral over the surface of partial t by partial r. Okay. Partial t by partial r is independent of theta and phi in the spherically symmetric system. Okay. It is independent of theta and phi. For the surface at a distance r from the origin, theta and phi vary between 0 to pi and 0 to 2 pi respectively. The integrand is independent of theta and phi. So, the integral over the surface just becomes equal to 4 pi r square. The surface area is 4 pi r square into partial t by partial r. Okay. And these two are just two different ways of simplifying the same equation. Okay. So, therefore, I get 4 pi r square partial t by partial r is equal to minus q by k. Okay. And I can divide throughout by 4 pi r square. Okay. And solve this equation to get t is equal to t infinity plus q by 4 pi k r. Okay. So, this is just another way of getting the same solution for a point source, except that now I have defined the point source as a delta function. Okay. I have defined the point source as a delta function of infinitesimal diameter, but with a finite amount of heat generated q per unit time from that point source. So, that the flux at the surface goes to infinity. You can see the temperature also goes to infinity proportional to 1 over r in this case. Okay. What is the advantage of defining this as a point source? Okay. The advantage is that now I can add up multiple sources. Okay. So, if I had a point source that was not at the origin, okay, but at some other location. Okay. So, if I had a point source that was not at the origin, but at some other location, x vector say, okay, it was at some location x vector. Okay. I will call this as xs, okay, as the location of the source, okay. Okay, the source location, and I wanted to find out what is the temperature at some location x. Okay. The only thing I need to do is to shift my origin to that particular location, okay, and at that particular location t will be equal to t infinity plus q by 4 pi k r, where r is now the distance between the source and the observation point. Okay. I just have to shift my origin to the source, and then the distance from the source to the observation point is the magnitude of x minus xs. Okay. So, this is just equal to t infinity plus q by 4 pi k into x minus xs. And if I were to write it in long form, I would get in component form into x minus xs the whole square plus whole square root. Okay. X square plus y square plus z square, the square root is the distance, and in this case the three displacements in the coordinate directions are x minus xs, y minus ys and z minus zs. Okay. I can get the flux q at any location is equal to minus k times the gradient of temperature. Okay. And the gradient of temperature is minus k into Ex partial by partial x plus Ey partial by partial y plus Ez partial by partial z, okay, of the temperature T. Okay. When I take partial by partial x of 1 over x minus x this whole thing to the half power, okay, that is the distance. Okay. When I take this, I will get, first I have to differentiate the argument in the denominator, which will be 2 into x minus xs, okay, divided by this to the minus half, right. So, I will get minus of half into this whole thing to the 3 halves. Okay. Whole to the 3 halves. Okay. And these 2's will cancel out after you done the differentiation using chain rule. First you differentiate this function with respect to x minus xs, and then you differentiate this function with respect to x minus xs the whole square, then differentiate x minus xs the whole square with respect to x. Okay. So, if you do this, similar expressions for y and z. Okay, so, I will get minus k into Ex into minus of x minus xs, okay, minus Ey into x minus minus Ez into z minus zs, the whole thing to the 3 halves power. So, this will be equal to k into x minus xs vector. My apologies here, I have, no, this is correct, yeah, okay, x minus xs the whole vector, which has these 3 components. Okay. It has 3 components in the Ex, Ey and Ez. Note that the negative sign outside and the negative side inside just give you a positive sign. Okay. And in the denominator, I have the 3 halves power of this function, which is the cube of the distance between the 2 points. Okay. So, therefore, I will have x minus xs the whole cubed. Okay. Okay. And then I have here a q by 4 pi. Okay. So, I should put that also. Okay. So, I will get this factor of q by 4 pi k in the expression for the temperature should be put in here, and from that I will get not k's will cancel out. factor of k will cancel out in both sides. Okay. And so this will give me 1 over 4 pi. Okay. So this basically, note that this flux is a vector. Okay. It has 3 components. Okay. Q by 4 pi into the 3 components are along the direction of the displacement vector. Okay. Okay. So note that at this point the flux will be along the direction of the separation between x and xs. Okay. And it is given by q by 4 pi into this x minus xs divided by x minus xs the whole cubed. Okay. So to summarize, due to a point source located at a particular location xs, okay, due to a point source located at a particular location xs, right, the temperature field is T is equal to q by 4 pi k into the distance between the observation point and the source point. Okay. The distance between the observation point and the source point, and the heat flux q is equal to q by 4 pi, okay, into x minus xs by the distance the whole cubed. Okay. This is for one point source. Okay. What if I had multiple point sources? Okay. What if I had multiple point sources? Okay. One at location x1 say, another at location x2, okay, another location x3 say. Okay. The heat flux at this observation point is going to be the sum of these 3. Okay. So the temperature will be equal to q by 4 pi k into x minus x1, okay, q1. So let's call this as an important point to note here is that the presence of these sources is not introducing any boundary in the flow, because these sources are of infinitesimal diameter. Therefore, the presence of these sources is not introducing any boundary within the flow. Okay. So therefore, I can just add up the point sources. Okay. That is the advantage of having a delta function source. I do not have to worry about applying boundary conditions on a domain of finite size, because these are all point sources. Okay. And the heat flux is once again the sum of the 3 heat fluxes. Okay. Q1 into x minus x1 by 4 pi into x minus x1 whole cubed plus Q2 And this can be done for any number of sources. An important point to note here is that the heat flux is the vector sum of the heat flux due to each of these sources. Okay. So for example, in this particular case, the heat flux from the source 1, okay, this will be Q1, it will be in the direction of x minus x1. Okay. Q2 will be in this direction, okay, and Q3 will be in this direction. The total heat flux at that location will be the vector sum of all of those three. Okay. The total heat flux will be the vector sum of all of these three. Okay. So, this is for a point source. Okay. I showed you how to get the temperature field for a point source, how to get the heat flux for a point source, first at the origin and then at any arbitrary location, and then after that how to superpose the temperature fields due to the point sources. It can be done easily in this case because these are infinitesimal point sources. They do not have introduce any boundaries within the flow. You cannot do that by substituting objects of finite size, because then you will have to satisfy boundary conditions on the object. You can do it only for point sources, and that is why the concept of a point source is an important concept in our discussion. Next, I will progress from point source to point dipole, and I will give you a physical interpretation of that. I will continue this in the next lecture. I will see you then.